So today we will be looking at the experiment resonance in LCR circuit. Now you might be wondering why we are having this experiment as part of this lab course. Because if you look at the other experiments, all those experiments are connected with mechanics, oscillations or waves. Now this seems to be the odd experiment out, but I would like to convince you first that this experiment is indeed related to what you are doing in the rest of the lab. So for that, I want to stress the analogy between an LCR circuit and a spring mass system. So let's find out what is the analogy between these two. Now, you know what is a spring mass system. So there is a spring and then there is a mass at the other end. Okay, and let's say there is some damping there. There is some viscous damping, right? So if you look at that system and compare with a circuit which has an inductor, capacitor and a resistor, you can see that the capacitor is analogous to the spring. Why? Because the spring stores potential energy and similarly the capacitor also stores potential energy, right? So then you can work out the rest of the analogy. So what is the mass analogous to? So the mass, you can show that the mass is analogous to the inductor, right? Because mass is inertia and essentially inductor is like inertia of the circuit because it opposes the change in current, right? And then of course the damping, viscous damping which is there over here is analogous to the resistance in the circuit. So now we have this complete analogy between the spring mass system and the LCR circuit. Let's go ahead with the experiment. But before that, I would urge you to look more closely at this analogy in terms of the equations. So we have the Newton's second law, the equation of motion for the spring mass system, and then you can write down a corresponding equation for the LCR circuit, which is nothing but Kirchhoff voltage law. Okay, you write down the Kirchhoff voltage law for the circuit, then you will see the analogy more closely. And in fact, once you write down the equations, you will realize that the displacement of the mass in the spring mass system is analogous to the charge. Okay, so I am not going into the detail of the Kirchhoff voltage law for the LCR circuit, that is given in the manual. So you should go through the manual and then realize the close analogy which is there between the spring mass system and the LCR circuit. Okay, so I am leaving out the details of the equations. I am not going into the equations. I will just look at the actual experiment, the procedure. So let's look at the procedure for the experiment. Now before we go into, before you actually go and start doing the experiment, you should have a circuit diagram for the LCR circuit. So the circuit is given in the manual. So before doing the experiment, you should just have a look at the circuit and then connect the circuit according to that. So let's first look at the series LCR circuit. All LC and R connected in series. So for this, we have a voltage source, alternating voltage source, which supplies an AC voltage at a particular frequency. Then we have R, then we have the inductor L, and then we have the capacitor. So all in series. But apart from this, you are also measuring the voltage across the resistor. Okay. So this is the circuit for the LCR circuit where all three are connected in series. Now once you are clear about the circuit, we should connect them according to this circuit. So let's now move and look at the circuit or rather the components of the circuit which are there in the laboratory. So here we have the different parts of the same circuit which we have just seen. So this is the voltage source which will produce a sine wave at a particular frequency. So I can set the frequency at which it will produce a sine wave. Now this is a voltmeter to measure the voltage across the resistor, and then here I have the resistor and then the inductor and the capacitor, all of them. Now what is left is to connect them according to the circuit diagram. So let's do that. So as you observe from there, from the voltage source, you move to the resistor. Now choose a minimum of 100 ohms, don't go for 10 ohms because the current would be very high in that case. From the resistor, you will have to connect to either the inductor or the capacitor. Since all three are in series, the order doesn't matter. So you I have connected one end to the inductor. Okay. Then from the other end of the inductor, I connect to the capacitor, and then from the capacitor, it will be back to the voltage source. Right? Now all three are in series, connected in series. The voltage source is in series with R, L and C. Fine. But I need to measure the voltage across the resistor. So for that I take the leads from the voltmeter and connect it across the resistor. Right? Okay. So now let's switch on all the equipment. Yeah. So now if you observe this display over here, it displays the frequency. Right now it is 1.60 kilohertz, and then the amplitude of the sine wave is also displayed. So if you notice these knobs, right now the knob at 50 K is pressed. That means the maximum frequency which I can generate is 50 kilohertz. But this is for a gross variation. For fine variation, I can adjust this knob, which will vary the frequency. So you notice that the frequency is changing. Now before we start the experiment, you should calculate the theoretical value of the resonant frequency. So that basically you should vary around that range, around the resonant frequency. Okay? Or the range of variation should include the resonant frequency. Fine. So I have now set it at 50K. Hopefully that will include the resonant frequency. And then you notice that the knob for sine wave is pressed. This instrument can also produce a triangular wave and a square wave, but we will go for sine wave. Fine. Now everything is set. So, and then you are looking at this display, which displays the voltage across the resistor. Now let's first do a fast sweep of the entire frequency range and check whether we are able to observe the resonance phenomenon. So I am now varying the frequency, then keep looking at the voltage. Now the voltage is increasing. So as I increase the frequency, the voltage is increasing. Okay, it has now reached 0.085. Now I go on for a frequency of 1.6. It is 0.123. And each time when you are actually doing the experiment and taking readings, you should vary it very slowly. Right now I am just checking whether the resonant frequency is included in the range of variation. Okay. So I am doing it very quickly. Later on we will do it very slowly and repeat it. So as we vary, notice that the voltage is going up. Okay. So it has now gone up to 0.158, and I go further. Okay, it is still increasing. Still increasing. Okay, it's in fact increasing even now. Slightly slower, it's not varying so fast, and if I go further, let's see what happens. Still increasing, but variation is slow. So now probably we are past the resonant frequency. So now the voltage is decreasing. So in fact, if you carefully record the readings, what you will observe is that the voltage across, if you plot, so actually what we will plot is the power dissipated in the resistor. If plot the power dissipated versus frequency, you will observe a plot like this. Okay. So here of course I have drawn a smooth curve, but what you will have will be discrete data points obtained at different frequencies. Now in order to obtain this kind of nice curve, what you should do is, first of all, you should vary, especially near the resonant frequency. Now this is the resonant frequency, let's call it nu0. So near the resonant frequency, you will have to be very careful. You will have to do a very fine variation or vary the frequency very slowly and give enough time for the instrument to settle down. Because each time you do a variation, okay, the voltmeter will take some time to stabilize. So do it slowly so that you are getting a steady reading. Okay. If the reading is not steady, if it varies between two values, you take the mean of those two values. Fine. And then do it slowly. But at the same time, if you are very far from the resonant frequency, so what is going to happen is that the variation is going to be very gradual. So you can afford to be careless there. So the idea is, since you have only a limited amount of time, you have to be more careful near the resonant frequency rather than somewhere very far away. Okay? And don't go for equally spaced values of frequency. There is nothing, no great merit in that. What you should do is, you should try to carefully capture the variation of the power around the resonant frequency. So that means you should take more readings near the resonant frequency and fewer readings when you are far away. Fine? That is the proper procedure. And therefore you should not go for taking readings at every 1 kilohertz or something like that. If you do that, what is likely to happen is that you will miss the peak altogether, and you, instead of getting a nice peak like this, you will get basically the peak will get chopped off. Okay, and you will get a much flatter curve. You will not actually be capturing the actual variation of the resonance phenomenon. Fine. So this is one thing you should keep in mind while taking readings. Be more careful near the resonant frequency. So this is the kind of graph which you will obtain, and obviously, as mentioned in the manual, you will have to repeat the experiment for two more different values of R. Right now we have done it for 100 ohms. Do it for, let's say, 82 ohms and 68 ohms, and then plot the corresponding curve. Okay. Why are we doing all this? So basically every oscillator, and this is also an oscillator, has what is called a Q factor. So the Q factor can be calculated from this curve, right? So I'm not going into again the details of that. That is there in the manual, how to calculate the Q factor from this graph. So I urge you to look at the manual and find out how to do that calculation. Fine. If you are done with this, let us proceed to the next part of the experiment, where we put L and C in parallel. So that is a parallel LCR circuit. But when I say parallel LCR circuit, it doesn't mean that all the three are in parallel. What we actually do is put L and C in parallel, and the combination is in series with R. So I will now redraw this circuit for the parallel LCR circuit. Okay. So what you need to do after drawing the circuit is to accordingly connect the circuit. So we now have this part of the circuit will be same, where I connect the voltmeter across the resistor, but then I want L and C to be in parallel. So this is the circuit for parallel LCR circuit. This is the second part of the experiment. And once you connect it like this, okay, which means you need to change it here. So you will have to redo the connections such that L and C are in parallel. So let's do that. So you need to basically, let's leave out this part of the circuit. Let's unplug this. Okay. So as before, from R, I need to connect one end to L. Okay. And if you look at this, the other end of L will go to the voltage source. Right. So from the other end of, I connected to L. Now I have to put C in parallel with this. So what we'll do now is put the capacitor in parallel with the inductor. So I've gone, one end is connected. Let's connect the other end as well. Okay. So now you notice that basically the C is in parallel with L, and the combination is in series with R. Okay. Now we switch it on. Let's see what is the difference in the case of the parallel LCR circuit. Now again, let's start with a very low frequency and then observe what happens when I do a sweep of the frequency. So I'm starting with again a low frequency, but now you observe that the behavior is very different. Earlier for a very low frequency we got a very low value for the voltage, but now you observe that the value of the voltage is much higher, okay, which means the power dissipated in the circuit is also higher. Now let's go for again a variation of the frequency. I again turn this knob so that the frequency is varied, and then you notice that the voltage value goes down, okay. So what you will observe is that as we vary the frequency, the voltage value is going to decrease. Initially of course the rate of decrease is small, but now it's decreasing much faster, and in fact it will go to a minimum at the resonant frequency. That's what you will observe, okay. So when you are actually doing an experiment, at each frequency value, especially wherever you observe there is a significant change, you pause for some time, allow those values to stabilize, and then note down the reading in your notebook, okay. So right now for 10 kilohertz I have got a pretty steady reading of 0.674, but obviously the resonant frequency we observed was closer to 16 kilohertz in this case for these values of LNC. So as we go towards the value of 16 kilohertz, you observe that this value decreases further and keeps on decreasing, and let's go towards the resonant frequency. So again remember that when you are close to the resonant frequency you will have to take more number of readings in order to get the true variation of the power with frequency, okay. So we are close to the resonant frequency, but it's still decreasing, okay. We are pretty close now, 15 kilohertz. So it has decreased to quite a low value. So here you have to vary it very slowly. So it's now stabilized at that value, 0.066 volts, 15 kilohertz, okay. Then let's decrease it further, still decreasing, right. So here is where you have to do it very patiently. Yeah. Now you notice that it has probably started decreasing. So that means we are crossing the resonant frequency. So around 16 kilohertz I am getting a value of 0.061 volts. So from your theoretical calculation you will have to confirm that for these values of L and C this is indeed the resonant frequency. So you can calculate the resonant frequency using the formula given in the manual, which is 1 by 2 pi root LC. So now you see that there is a clear trend, this value is going to increase, and so you need not go all the way up to 50 kilohertz. That is another thing. We observed that the resonant frequency is around 16 kilohertz. So probably you can stop when you got the variation. So now what will this variation look like? So if you plot a graph of the power dissipated versus frequency, this is going to be a dip, and then there will be a minimum around the resonant frequency, okay. So probably if you go to high enough frequency, the curve is going to become pretty flat. At that point you can just stop, fine. Yeah. So that is probably like around 30 kilohertz or something. You don't have to go all the way up to 50 kilohertz. So whenever you observe that the variation in the value is not much, you can stop the experiment at that stage, and then you will have to repeat it for a different value of R. So there is one more thing which you have to keep in mind while doing an experiment, especially when you are encountering a new setup. In the voltmeter, you might see that there are some knobs here. This is a multimeter actually, okay, which means you can measure various things like resistance, voltage, current, and so on, and even capacitance. So you will have to set the knob. Make sure that the knob is set for measuring a voltage and an alternating voltage. It can also measure direct voltage, but you have to set it here. And here if you notice I have set it at 20 volts, which means the maximum voltage which it can measure in this setting is 20 volts. Now, what can happen if you don't set it properly is that, suppose I set it at a lower value, the lower value lower than this is, let's say 2 volts or 200 millivolts. If I set it at a very low value, then what is going to happen is that, in the case of series LCR, when I come near the resonance, it is going to overshoot and go beyond the full scale. Then what would you do? You would change the scale. But that's not a desirable thing. You should never change the scale while measuring voltages. So you should have the same scale throughout the experiment. Which means, that is why we do the rough sweep, to figure out what is the range of voltage values you will get when you go across the resonant frequency. So please don't change the scale. Ensure that a single scale is enough to capture the entire variation in the voltage values. So that is another thing which you should keep in mind. So apart from that, suppose you notice that the value is not steady like this. Probably what is happening is that there is some loose connection. Okay, so probably you can try to figure out where is the loose connection. You can just try pressing something is loose, so you press it. Let's say the connection becomes tight, then probably the value will stabilize. So of course, if beyond that you are not able to figure out the problem even then maybe you can seek help. But I urge you to experiment. I mean, not only do the experiment in a mechanical manner, but also try to figure out where are the problems. Do some amount of troubleshooting on your own. Okay, I hope you are now clear about the procedure for doing this experiment where you are studying the resonance in LCR circuit. Thank you.